Okay, cool. And so this week we're going to dedicate to sort of reviewing Chem 128 material, in particular the stuff that's really important for this course. We're going to talk mostly about just the organic structures as well as nomenclature. That'll be kind of our big focus on today, making sure we got the same set of rules for nomenclature. Nomenclature is something that won't be going away, right? So pretty much every chapter we're introduced to a new functional group. Every new functional group has some new nomenclature to learn. The good news is once you get like the base rules of nomenclature down, adding a little rule here and there is not a big deal, okay? Functional groups, I'm going to leave this to you. There is a posted video that goes through them. At this point, your main goal is to be able to spy all the different functional groups that we discuss in organic chemistry, right? So just kind of looking at a molecule, can you tell me what functional groups are present, okay? All right, cool. So let's get started here. Organic chemistry, you all graduated to these zigzaggy line structures here. So step one, everybody's going to give me the molecular formula for the molecule that I put down here. Meaning this is a hydrocarbon with a formula C something, H something else. I want to know what that molecular formula is given this structure here. Okay, we're going to play that game with a few of them. Cool. So this is this like shorthand that we use for drawing organic molecules. I mean, literally the only reason it exists is because of laziness, because we draw so many molecules in organic chemistry that trying to draw their Lewis structure would be very miserable. The way that these bond line structures work is that we have these carbons that are implied at every endpoint and intersection. All right, so what do I mean by that? How many carbons do we count in this structure here? 6, because every endpoint, 1, 2, 3, and every intersection of these line points, 4, 5, 6, these are all carbon atoms, right? So endpoints and intersections are where the carbons live in our bond line structure. Okay, the hydrogens are also implied. But filling in the hydrogens is actually a little bit trickier here. All right, we're going to fill in with those hydrogens to give all carbons that complete octet of 4 bonds. Okay, carbon, one of the nice things about organic chemistry is our focus on these smaller elements on our periodic tables. Carbon, nitrogen, oxygen. And they have these hard, fast octet rules that they never break. Carbon always will have 4 bonds, right? So when we look at this structure here, we just need to make sure that every carbon here has 4 bonds. So if I look on the endpoint here, it's already got 1 carbon-carbon bond explicitly drawn. I need to fill it in with these 3 extra hydrogens. Right? Same with all these other endpoint carbons here, what we would call methyl groups. Each one has 3 hydrogens in order to complete its octet. What about these 2 in the middle? How many hydrogens do I need? 2. And what about this one in the middle of this little Mercedes symbol thing? 1. Just 1, right? So it's already got 3 bonds explicitly drawn. All right, so if we count them all up, our molecular formula here should be C6H14. All right, same game with here, but now we have what we would consider, what functional group is this? Alkene, all right? So this carbon-carbon double bond, one of the first ones that we studied for reactions last semester. We're actually going to pick it up and discuss alkenes a lot at the beginning of this semester as well. All right, so how many carbons do we see here? 4. All right, we'll just highlight those in orange here. Okay, we need to fill in our hydrogens, these N ones here. Need 3. All right, and what about the 2 in the middle?
1.
Just 1, right? So we already got, let's count them off here. 1, 2, 3 carbon-carbon bonds. So we just need 1 more hydrogen on each of these in order to square that away. So our formula here is C4H8. All right, and then lastly we have this carbon-carbon triple bond, an alkyne. How many carbons do we see here?
6.
I'll say the triple bonds trip people up quite a bit. As soon as you see that triple bond in your mind's eye, you want to note that there are carbons on either end of that triple bond. It's just people tend to forget about those carbons. We also want to note how we draw our alkyne geometry. Specifically, it's linear about that carbon-carbon triple bond, right? So all 4 of these carbons, if we draw this molecule properly, all 4 of those carbons should be in a straight line, that linear geometry about that triple bond. And 5, 6. Cool. All right, we're going to fill in with hydrogens. Okay, again, our endpoints here each need 3. What about this one here?
1.
Just 1. And what about the carbons about that triple bond? They're already good. They already got 4 carbon-carbon bonds going on. If we just want to look at one in particular and count it off here. 1, 2, 3, 4, that carbon's already satisfied. Okay, so our formula here, what do we say? 6H10. Cool. So we are pretty much explicitly going to be looking at bond line structures here in this class. So let's make sure that we're familiar with how to draw these as well as how to interpret them. Cool. Okay. Another thing that's going to kind of come up, especially pretty quickly when we talk about our carbon-carbon double bonds again, is what's called hybridization. Okay. In order to figure out the hybridization of each carbon, so first of all, I guess what do we mean by hybridization? We have atomic orbitals that mix to form hybrid orbitals. Right? So if we just take a carbon atom all by itself, where does the electrons in that atom live? They live in the s and p orbitals, right? If you remember back to Chem 1A, you would look at the periodic table and you would say 1s2, 2s2, 2p2, right? That was the electron configuration of that atom. That tells you where the electrons in that atom live. Well, as soon as you take that atom and you start making bonds with it, it takes those atomic orbitals and it mixes them together to form these hybrid orbitals, okay? And these hybrid orbitals are important because that's how we interpret the shape as well as the bonding behavior, the pi and sigma bonding business of our molecules, all right? So this determines shape and bonds, sigma and pi. All right, so let's take our same examples here. Our alkane, if we just want to pick one of these carbons, they're all going to be the same actually. These are what we would call sp3 hybridized. Okay, so alkanes, all sp3 hybridized. As well as all sigma bonds. We'll go and take that same example of our alkene. Okay. To be clear, two of these carbons are still boring old sp3 hybridized, but the two that are about that carbon-carbon double bond, these are now, what did I say about the red ones? sp3 hybridized. Oh, okay, rewind. Two of those in red are still boring old sp3 hybridized carbons, but the two that are about that carbon-carbon double bond are sp2 hybridized. All right. And that's important. One of those carbon-carbon bonds is a boring old sigma bond, but the other one is one of those highly reactive pi bonds. Okay, and then if we take an alkyne, again, these two on the end are just boring old sp3 hybridized. But now these two that are about that carbon-carbon triple bond are now sp hybridized. That carbon-carbon triple bond will consist of one boring old sigma bond, but now it's got two of those highly reactive pi bonds. All right, so in an alkane, those carbons take their s orbital and mix them with all three of their p orbitals to be sp3 hybridized, and that will consist only of sigma bonds. If you have an alkene, that carbon-carbon double bond is between sp2 hybridized carbons, and that carbon-carbon double bond consists of one sigma and one pi bond. Again, the thing that we want to note here is that the pi bonds are more reactive. A lot of our understanding about the reactivity of alkenes is due to these pi bonds. All right, and then if we form an alkyne, now all of a sudden those two triple bonded carbons are sp hybridized, and they have two pi bonds, so they can react twice as much. You would have found that these, again, more reactive. These undergo very similar reactions to our alkenes, just twice as much, right? Twice the equivalence in your addition reactions of your alkenes. Cool. All right, so we're going to move on. We're going to talk about nomenclature. And what we want to do is kind of lay down a list of initial rules that we need that we can use, rinse and repeat over and over again every time we come to a new functional group. All right? So let's take a simple example here. We're going to kind of work through some more and more complicated examples. All right, we're always going to break this down into the same 4 steps for our nomenclature. All right, step 1 is you need to find what we call the parent chain. That's the longest continuous set of carbons. All right. So what we need to do is we have this set of prefixes. We're going to make a little table here, a little cheat sheet to have in our notes. Number of carbons and the prefixes we use. All right, so 1, we use the prefix meth. 2 is F. 3 is prop. And 4 is bute. All right, and these are kind of the 4 weird ones that are very unique to chemistry, right? These 4 prefixes. Meth for 1, F for 2, prop for 3, and bute for 4. The rest of these are Greek or something? I don't know. But anyway, you also see them in your geometry course as well. So 5 is pent, 6 is hex, 7 is one that trips people up, hept, H-E-P-T. 8 is oct. 9 is non, and 10 is dec. Let me make some room. Okay. So step 1, we got to find our parent chain, our longest continuous set of carbons. All right, so in this example here, how many carbons are in that parent chain? 5, we got just this one straight chain alkane here, 1, 2, 3, 4, 5. So we're going to use the prefix pent, all right? And then what ending are we going to stick on the end there is going to depend on the functional group in that molecule. So we're going to stick to alkanes here today, and alkanes have the ending ANE. Different functional groups will have different endings. We'll tweak these rules ever so slightly as we go throughout this course, all right? But the main thing that we're going to change is just the suffix that we use to refer to that particular functional group. So this one here, we're going to take that prefix for 5, pent, and we're going to stick that ANE ending on, giving us our molecule's name, pentane. Okay. All right, so in this particular case, we're done, right? This was a particularly simple molecule, a straight chain alkane. It only consists of that parent chain, so we're done at this point for this one. All right, so let's move on to another example here. And now we're going to throw in a branch point. Let's do this one. All right, again, always going to have that same first step. So everybody take a second, find my parent chain for this molecule. All right, how many carbons in that parent chain? Again, 5. Cool, but the entire goal of nomenclature in organic chemistry is to uniquely account for everything in that molecule, right? So I still got to account for that other carbon here. So now we're going to lay out our other 2 rules. Next, we're going to find and name what we call our substituents. Anything that's sticking off of that parent chain. All right. For what we call alkyl substituents, meaning they're just carbons and hydrogens, you're going to use the YL suffix along with that prefix that corresponds to the number of carbons. All right, so in this example here, we got our parent chain in orange. I still got to account for this extra carbon up here. There's only one of them, so it gets that meth prefix, and it's an alkyl substituent, so this would be a methyl group. Okay? I'm going to leave a little bit of space. We're going to introduce a few other substituents here today. Notably our halogens, not too crazy, but we want to make some room here. Okay? The next step is we got to indicate where that substituent is on our parent chain. We're going to number our parent chain. All right, and we're going to number our parent chain in such a way that we get the lowest number in our final name. All right, what do I mean by that? So my parent chain, you can always number two different ways, front to back, back to front, right? So I can either say 1, 2, 3, 4, 5, or I can go the other direction, 1, 2, 3, 4, 5. All right, and I'm going to look at these two numbering schemes, and I'm going to pick the one that gives the lowest name, the lowest number in my name. Puts that left methyl group on the lowest number carbon. So what do I want, red or blue? Red. I want my carbon number 2 to be the location of that methyl group. All right. So now the last step is we got to assemble that name. All right, you're going to put your substituent, rather you're going to put the locant, that number, dash the substituent, followed by the parent, all run together in one word. All right, so my locant was that number. My substituent name I had in green there, that was my methyl group. And then my parent chain is that 5-carbon alkane, my pentane. So if I put this together here, this would be 2-methyl pentane. All one word, all run together. All right. Cool. All right, let's do a few more and then we'll complicate things a little bit. examples. Take a few minutes, see if you can't name these. We will talk about these halogen groups in a minute. If you can remember, fantastic. Let's focus on these top two first. We need to go through and find that longest continuous set of carbons. 2, 3, 4, 5, 6. I'm going to be good and double check. 1, 2, 3, 4, 5, 6. All right, in that case, it does not matter which one you pick to be your parent chain. They're both equivalent. Cool. All right, so now we're going to find and name our substituent. This alkyl group here now contains 2 carbons. So what would be the name of that substituent group? An ethyl group. Cool, now we're going to number that parent chain 1, 2, 3, 4, 5, 6, or you can go the other way. 1, 2, 3, 4, 5, 6. And which one of these numbering schemes do we like better, red or blue? The blue, because that's going to put that ethyl group on that lowest possible number. All right. So then we're going to assemble this together. That locant goes first. 3, substituent name ethyl, and then my parent chain being 6 carbons long will be a hexane. So 3-ethylhexane. All right, now let's do this one. How many carbons in my parent chain here? 8. Cool, so now I got 2 branch points, 2 substituents here. This one with its 1 carbon, we did this example before. This would be a methyl group. And what about this one with 1, 2, 3 carbons? That would be a propyl group. All right, so now we're going to number 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Which one do we like better, red or blue here? Okay, cool. So to be clear, one great idea if you're having trouble seeing is to just list them off. If I picked my blue numbering scheme, I would have a 4 and a 6 in my name. If I pick my red numbering scheme, it would be a 3 and a 5 in my name, right? So this makes it clear that that red numbering scheme is going to put the lower number in my name. That's what I want out of my numbering here. All right, so one more rule. We're going to go back here because now we have two substituents. So when we assemble our name, we're going to play the same game here. All right, but we have to assemble the substituents in alphabetical order in that name. All right, not numerical order. It doesn't matter what my locants are. We're going to put those substituents in alphabetical order. So I'm going to look and I'm going to say, all right, LMNOP. There we go. Methyl comes before propyl in the alphabet, so that's going to be how it is in my name as well. So I'm going to say 3 methyl, 5 propyl, and then we have an 8-carbon parent chain here, 8-carbon alkane, so octane, right? 3 methyl, 5 propyl, octane. All right. Again, our substituents are in alphabetical order. Importantly, no spaces in the name, right? This is all run together as one word. The other thing you'll notice that we have these dashes here. These dashes are only going to be in your name to separate out the letters and the numbers, right? I don't have a dash between propyl and octane, for example. Okay, a very common mistake. All right, so now we got some halogens here. So let's go back and remind ourselves. We have special names for these halogen substituents. All right, in the world of nomenclature, your halogens aren't treated as functional groups. They don't go at the end of the name. They go at the beginning of the name, just like a methyl group or an ethyl group. They're treated as substituents in the nomenclature. And they each have a special name. So our fluorine is a fluoro group. Our chlorine is a chloro group. Bromine is a bromo group. And iodine is an iodo group. All right, these alkyl halides, these alkanes that have halogens in them are also one of the functional groups that you studied last semester. They turn out to be great starting points for a synthesis because for a variety of reasons, that halogen is kind of easy to replace, to break off of there and replace with something else. Cool, so give these last two a try, given what we just discussed about how we name those halogen substituents. All right, so first of all, this is our first time seeing a heteroatom in our structure here. By heteroatom, I mean everything other than carbon and hydrogen, right? So in organic chemistry, that's what we call our heteroatoms, and we have to draw them in explicitly. Our carbons and hydrogens, they're implied in our bond line structure. Everything else, you'll explicitly see the chemical symbol for, okay? So how many carbons are there in this molecule here? There's 4, all right? So 1, 2, 3, 4. Importantly, we draw these carbon-bromine bonds explicitly. There's not carbons that live at the end of those, right? All right, and then we have this. We called these bromo groups. We're going to number our parent chain. In this case, we're going to go this direction here. So those 2 bromo groups live on carbon 2. All right. Importantly, now that we have these 2 identical substituents, how are we going to refer to those in our name? Dibromo. All right. So let's just make a note here. For identical substituents, we need to use those prefixes. And of course, they're different than our number of carbon prefixes, just to make it difficult here. All right, so let's say for multiple identical substituents, we're going to use these prefixes di, tri, tetra, penta, hexa. That'll be good. Hepta, octa, all right? But you probably won't encounter that, having 8 identical substituents. All right? The other thing that everybody always forgets here is you need to include the locant of both of those bromo groups in your name. You can't just say 2-dibromo. Since there are 2 bromo groups, you have to indicate that they are both located on carbon 2, 2,2-dibromo butane. All right, and then notice how we space out numbers in our name. We put commas between to separate our numbers, and we use those dashes to separate letters and numbers, right? So 2,2-dibromobutane. All right, let's do this one together here. How many carbons are there in that parent chain? 5, 1, 2, 3, 4, 5. We called this a chloro group, and we called this a fluoro group. All right, we're going to now number our parent chain. 1, 2, 3, 4, 5. Go the other way. 1, 2, 3, 4, 5. All right, and now we have a bit of a problem, something that we haven't encountered before. If I use the blue numbering scheme, what 2 numbers would be built into my name? A 2 and a 4. And if I use the red numbering scheme, what 2 would be built into my name? A 2 and a 4. All right, so if and only if there is a tie in your numbering scheme, you're going to break that tie with alphabetical order, okay? A lot of people mistakenly jump to alphabetical order right off the bat, all right? The first rule is lowest number in the name. Then if there's a tie, you break that tie with alphabetical order, okay? So let's just add that to our numbering of our parent chain. Number 1, most important, lowest number in the name. Number 2, we're going to say if there's a tie, we can break it with alphabetical order. All right, so everybody take a second, see if you can't finish off the name for that molecule that we were working on. right, so 2-chlorofluoropentane. All right, these organic chemistry names, they really roll off the tongue, huh? I don't think anybody's like gonna name their pet after one of these molecules up here or anything like that, but the whole point of this system is that it will uniquely point to one structure. One structure will match that name, and it accounts for all of the carbons and the heteroatoms in that molecule. That's the goal with our organic chemistry nomenclature, okay? One other thing that we're gonna discuss here with regard to nomenclature, kind of a special case. It's going to be important because we're going to see this come up later in the semester as well when we have these branched alkyl substituents. Okay. All right, so what do we mean by our branched alkyl substituents? If we follow our normal rules for nomenclature and we find our parent chain, we would find that the longest continuous set of carbons are these 9 here. All right, so now we have this substituent here, but this substituent has this branch point on it. All right, so we have a few different ways of dealing with these. All right, some of them, some of the most special ones, have what are called common names. All right, and this is the one I want to do a specific example of. There are a few, so I'm going to give you sort of a cheat sheet here. A few of them have slightly different names, but this little fork at the end business always falls under this same naming pattern. These are what we call iso groups. And they have that fork at the very end. All right, and how you name these iso groups is the word iso followed by the total number of carbons. All right, so what do I mean by that? This thing here with its 1, 2, 3, 4 total carbons, all right? The total number of carbons in that name or in that group, this would be an isobutyl group. If there was a total of 5 carbons, it would be an isopentyl group. A total of 6 carbons, isohexyl group, right? If it's got this little fork at the end, you count the total number of carbons and stick that word iso in front of it, okay? So for these ones that have a special common name, you can use that common name just like you would any other substituent name. So we could call this thing here 1, 2, 3, 4, 5. This would be 5 isobutyl nonane. All right. However, not everything has a common name. All right. We can come up with many branched alkyl groups that don't have that. And so don't you worry, the IUPAC has your back here. They have a way to deal with this. All right. We're going to call these our IUPAC names. To be clear, the IUPAC is the International Union of Physical and Applied Chemistry, and there who comes up with our nomenclature scheme for organic molecules. All right, so we're going to do the same thing, but give it its IUPAC name. And we've already found our parent chain, right? Check, check. It's a nonane. All right, so now we're going to look only at that branched alkyl substituent. And we're going to play the exact same game that we played before. We're going to find our longest continuous set of carbons. All right, so now looking only at this portion of our molecule here, right? We're going to find that longest continuous set of carbons. So 1, 2, 3. Okay, we're going to number this set of carbons, but this is the one place where we need to be careful here. Our rules for numbering is that carbon 1 has to be attached to that parent chain. Right? So whatever's actually sticking off of that parent chain, that becomes carbon 1. So we're going to number with carbon 1 on that parent chain. All right, then this group sticking off here is like the substituent of the substituent here, a 1-carbon methyl group. All right, it's located on carbon 2 of our branched substituent here. So my name, my IUPAC name for the substituent is 2-methyl-propyl. Notice that we keep the YL on the end here because it's still not my parent chain. All right, and then the last kind of annoying thing is when we build this into our name, we have to indicate where that branched alkyl group is. It's located on carbon 5, so we're going to say 5, and then in parentheses, 2-methyl-propyl nonane. All right, and we're going to see these branched alkyl groups in a future chapter, so we just want to remember how we go about naming these. Okay, as a reminder, in any of these review assignments, the textbook that we're using is that free online textbook. You can download a PDF copy on Canvas. Everything that we did at the beginning, our organic structures, is literally located in the very first chapter of that book. Okay, this nomenclature business starts off in the alkanes chapter, which is like 7, I want to say. But maybe don't quote me on that and look in your table of contents. Cool. All right, we'll pick up with this next time. We're really going to focus on electron pushing arrows, reaction mechanisms next class. They're going to be an important part of this course.